In this lecture, we are going to talk about deBroglie's hypothesis. But before we discuss deBroglie's hypothesis, we should know that how this hypothesis has arrived. Now we know that light is dual in character. So when you say dual in character, what do we mean by light is dual in character? It means that there are several phenomena of light. For example, reflection, refraction, interference, diffraction. To explain this phenomenon, we need to consider light as a wave. But there are other phenomena like photoelectric effect, Compton effect, where to explain those phenomena, light is considered as a particle. So depending upon the nature of the experiment, light is taken either as wave or particle. So the wave nature and particle nature both cannot be possible simultaneously, but it depends upon which phenomena you want to know about. So taking this into consideration, deBroglie thought that why we should stick with only light. That means that light which is behaving as a wave and also as a particle, later on it was named as photon, why it is not for other particles like electron or any other particles. So deBroglie thought that light possesses both wave and particle nature. Similarly, any particle made of matter will behave both as matter as well as wave. Or in other words, he said that waves must also be associated with material particles. That means waves associated with material particles are known as matter waves. So if you have particle, whether it's electron, proton or any other bigger particles, this will also possess, or these particles will also possess waves. So taking this concept, deBroglie tried to calculate the wavelength which is associated with the wave of the particle or wave, and he related with the momentum of a particle. So the formula was lambda is equal to h by p. Well, lambda is called the wavelength of the particle, associated wave with the particle. Wavelength of the wave associated with the particle, h is Planck's constant and p is the momentum. So if you have a mass, particle of mass m moving with velocity v, then the kinetic energy is given by half m square, which we can write down as in terms of momentum, which is p square by 2m, where p is the momentum. And we also write momentum is equal to root over 2me from this relation. So if we substitute the value of lambda is equal to h by p, where h is Planck's constant, we finally arrive into a relation between velocity and wavelength. So we can say that wavelength of the particle or wavelength of the wave associated with that particle is inversely proportional with the momentum or the energy or the velocity. So now the question arises that what about any particle? What about microscopic particles or macroscopic particles? Is this deBroglie's hypothesis valid for any particle? Yes, it is valid, but when you talk about macroscopic particles, that means if you substitute the value of, say, momentum or velocity of a macroscopic particle, the wavelength associated, that means the wave produced and the wavelength associated for a macroscopic particle, which is 10 raised to minus 24 Armstrong, and this wavelength is nearly impossible to measure. That means for a macroscopic particle, though a wave, for that particle a wave can be produced or it is associated with a wave, but the measurement of that wave is not feasible. Whereas in case of a microscopic particles like electron, proton, if you calculate the wavelength of that particle, a wave of that particle, then it comes around 10 raised to minus 10 meter, and which is feasible to measure. That is why de Broglie's hypothesis is targeted for the microscopic particles. That means to know their mechanics, de Broglie's hypothesis can be used. So if you have, what would be the de Broglie's wavelength for a charged particles? De Broglie's wavelength for a charged particles can be related as, if you use this formula lambda is equal to h by p, we can substitute the value of p as root over 2me, where e is the kinetic energy. If you want to have this kinetic energy expressed in terms of potential, so how do you get it? Let us say that a particle, a charged particle, is accelerated by a potential difference of v, and the charge of that particle is q. Then we can write that the kinetic energy is equal to half mv square, which is also equal to qv, because this is the amount of energy given by the potential to run, or this particle will undergo a kinetic energy of half mv square. So if you substitute this relation, lambda is equal to h by p, and in place of p, the momentum, we express in terms of kinetic energy, and then finally we can express also in terms of potential difference. So for an electron, as an example, we can calculate the wavelength. Electron being a charged particle, we can calculate the wavelength, substituting the value of Planck's constant at 6.610 raised to minus 34, and the charge and mass of electron, if you substitute, we get the relation that lambda is inversely proportional to 1 by root over v, where this capital V is the potential difference. So now the question is that how does this de Broglie's relation was explained? So de Broglie, according to de Broglie, electron revolves around the nucleus in the form of a stationary waves, like similar fashion, like stationary waves in a vibrating string. So if you just make this circular orbit and you straighten it, it's like it will behave as a stationary waves of a vibrating string. So if you consider that the number of complete waves that is produced in a revolving electron in an orbit, then we can write down that 2 pi r, the circumference of that orbit, is equal to the n number of wavelength. That means the n number of complete waves. Now if you use this relation, that means electron can stay in this circular orbit, so circumference is an integral multiple of de Broglie's wavelength associated with the electron. So if you take this relation lambda is equal to h by mv and substitute the value of 2 pi r is equal to n lambda, we get mvr is equal to nh by 2 pi. So this is actually also called the angular momentum is integral multiple of Planck's constant. So this is also Bohr's quantization condition. So here we come to the end of this lecture on de Broglie's hypothesis.